Hello all and welcome back to this course on computer organization. So having looked at the 5-stage pipeline processor construction and also having just looked at the control unit very briefly, we just said that the control unit is the same as that of the single cycle processor. Control signals generated just flow through flip-flops and then drop off wherever necessary. So this was stated in a very simple manner, but it's also good for us to understand the flow of these control signals and the data through a pipeline processor. Of course, doing it for a 5-stage pipeline might be a little it's a quite a difficult task for us to draw all those signals. So I think it's a good idea for us to look at a very simple 2-stage pipeline. Okay, that also helps us understand that the choice of phi is not sacrosanct. Okay, it is not necessary that you have to make only 5-stage pipelines. You can as well have smaller or more stages of pipeline. It really depends on delay, your architecture and so on. So what we are going to do now is we are going to come up with we are not going to draw the entire 2-stage pipeline from scratch. What we'll do is we'll start with this very simple block diagram that we came up with for the 5-stage pipeline, and I'm going to eliminate some flip-flops from this whole thing. First thing I'll do is I'll eliminate this flip-flop after the instruction memory. Okay, so what does this do? It basically says that the signal from the instruction memory can flow in directly to the register file and decoder controller, right? Earlier, what the output of the instruction memory was, the read from the read port was basically called INSTR. We now added the flip-flop and therefore called it INSTR-D. Of course, if you are bypassing, we can as well call it INSTR, but I'll just leave it as INSTR-D for brevity now. Likewise, this program counter, right, can simply come out directly as whatever the fetch and it can the PCF or PCD. I don't really care. I'm going to leave it as PCD. Likewise, I'm going to bypass this guy here, right? So the PC plus 4 also can just be called PC plus 4D signal, right? The only flip-flop that I'm actually going to retain is this particular flip-flop that appears right after the register file. Why specifically this? Because it is a very nice, it also takes care of registering certain control signals. So if I had kept only this flip-flop, then the control unit is not very different. It's after that, and then that is simply going to remain combinational. It doesn't help us understand control signal flow through a pipeline. So therefore, deliberately I am choosing the flip-flop after the register file as the only flip-flop in this particular 2-stage pipeline system, right? And of course, the design is not going to be very different. You're going to have signals just flowing through it like that. Then I am going to get rid of both these flip-flops. Okay, so which means that the ALU result will simply bypass the flip-flop, go through directly as ALU result E or ALU result M. Write data E will come out like this. Okay, likewise this also will bypass, right? Then this signal will go through because you're skipping that flip-flop, so the ALU result can bypass and just go in as ALU result M or ALU result E actually, right? Because that's all we have out there. Likewise, this data from the data memory, which we are going to call as read data, it would have been called read data M or read data W, but I can also call it read data E. Okay, actually, because it is happening now in the same execution unit. Likewise, this will bypass, so will this, and then this will also bypass, right? So effectively what we now have is a very nice simple pipeline where we are doing instruction fetch, okay, fetch, okay, and then we are doing a decode, right? So this is the decode, D. Then we are doing execute. Okay. Then we are doing data memory. Right. So this is E. This is DM. Right. And the last stage is of course the RF write back. Okay, this is the WB, right? So the operations execute, data memory and write back are combined into one big combinational block, and the fetch and decode is also combined as one big combinational block. Now the key thing to note here is that the timing wise this might not be the most optimal thing, right? So the clock frequency here will most likely be determined by this execute, data memory, write back and all that, but that's not the point of this discussion. We want to just look at the instruction, the control flow and the data flow through this whole thing. Okay, so we can look at a typical instruction that we wanted, right? So let's just look at that. Let's start with this kind of an instruction flow. Okay, this is what I am showing you here is the familiar 5-stage pipeline timing diagram. Okay, but we'll modify this now so that this will become the 2-stage pipeline. Okay, so what are we going to do? We are basically we are getting rid of this particular flip-flop. So therefore the add will just go through like this. Okay, this is the only flip-flop that is going to remain in our pipeline. Okay, and therefore this whole timing diagram is now going to get redefined a little bit. Okay, let's look at it. This is my time, right? So if you look at it, my instruction fetch and register file is basically the first clock cycle that we are talking about, right? This is my first clock cycle. This flip-flop, right, is the only flip-flop that is going to register my data, and then I have so this is my fetch plus decode operation. Okay, and here we are talking about execute, data memory and write back in the second clock cycle. So technically this is my second clock cycle. So this doesn't exist anymore because that is for the 5-stage pipeline. My clock cycle is 1, 2. Okay, and where do the other instructions happen? Well, that has to get offset significantly. So we will have to draw this again. So we will consider only these 2 instructions, a very small subset of instructions. We are going to look at add, okay, S8, S4, S5 and subtract, okay, S2, S8, S3, 8, S3, right? So the way this is going to happen is this will take 3 clock cycles now to finish the execution, these 2 instructions. Why? Because it will take 2 clock cycles for the add instruction to happen, but in the second clock cycle the fetch and decode of the subtract would have been initiated, and then one more clock cycle the execute, data memory, write back will basically happen, right? So therefore if I look at this, I can draw the clock cycles here, right? Clock cycles out here. Okay, So the instruction memory is going to, allow you to read the data here, right? You've got that instruction, okay, and then you are basically going to the register file. So I'll tell you what that thing is, okay. I will just call it RF, okay. I will not worry about shading it right now, okay, or maybe I should, because you will not be able to differentiate between an unused cycle and this, okay. So if you look at this, register file is shaded only half, okay, so I might need a different color there. So instruction memory and register file, and this is the shading is going to indicate the usage, okay. And then what is going to happen, this is going to go into my execution unit, and this spills into clock cycle 2. This is my clock cycle 3, okay. So effectively, if I were to sketch the clock here, it would look like this. Okay, this is the rising edge, right? So this is my rising edge. So this is cycle 1, 2 and 3. So here is where the ALU will kick in, okay, and the register file is going to give you data, okay. That is going to, basically the source registers are S4 and S5, and this is then going to go through the ALU. Then it is going to bypass the data memory because there is no data memory operation happening. So this is DM, which is not shaded. This guy has to be shaded completely. So the DM can be in red, right? Data memory. And finally, this is my register file write back, okay. So RF, write back, okay. And if you look at it, that is also called RF, okay. But this is, I am going to shade it in the first half, okay. By the end of this discussion, you will understand what this shading first half, second half also means for the register file. So we have been able to do this, and at the end of this cycle, if you look at it, it would have finished the answer here would have got the answer would get written back into S8. So if you look at it, this is S8. So you are doing S4 minus S5, okay, and of course the S4 plus S5. So therefore the operation that is being performed in this cycle is the plus, because the ALU is now trying to do add operation corresponding to this, okay. Now if you look at the subsequent cycle, right, in cycle 2, when the ALU is executing, data memory write back is happening, the instruction memory and register file decoding of the previous of the next instruction, subtract, will basically kick in here. So if you look at this, what is going to happen is your instruction memory will get read here, instruction memory, and then I have a register file out here as well, right. So here it is, this is my register file, and this is happening again in one half of the clock cycle, okay. So the instruction has come in, gone through the register file, and it is able to give you 2 arguments into the ALU as usual, right. So here it is, and therefore this is a subtract operation this time, okay, because you are doing a subtract corresponding to this, and then you are going to shade this entirely because it is going to be used. It's going to be used fully. Okay, so we have to see what all of these things mean here, right? And then you're going to come out here. Now the important part is this has to be S8 here and this has to be S3. So you see that this S8 and this S8 are basically the same register. So in some sense you are writing the result back into that register and then you are trying to read back, you are trying to read out of this particular same register, and that can cause problems, by the way, which we will address a little later, right? So then you go through again the data memory, which basically has no operation here, okay, and that's why I am not shading it. And then finally I am going to come back for my register file like this. Maybe I'll draw it smaller, okay, RF, and this operation is what we are trying to see here, okay. So this is the sequence of operations that are happening on the data path, okay. The S8, the sources S4, S5 are getting decoded by that register file. You are getting the contents of S4 and S5. So remember, the contents of S4 and S5 are actually appearing in the second clock cycle only. So the actual execution of that instruction is happening in the second clock cycle, during which the instruction fetch and the register file decoding can happen for the second instruction, right? So now what we should also do is to trace some of these control signals, okay. So what we are going to do now is we are going to look at, okay, when this add instruction comes in, it decodes, right? So this control block is going to do some decoding. In the first clock cycle, the fetch and decode is happening for the add instruction, right? And therefore, if you look at it, the ALU control instruction itself, right? ALU control instruction will get decoded in the first clock cycle itself for the add instruction, right? So you look at this here. So first thing to note is the ALU control instruction. Maybe I'll draw that in magenta. ALU control. So what is going to happen? This particular clock cycle, let me just mark that here, right? Right. So I have the first clock cycle here. The ALU control has sort of been decoded in parallel to this register file operation. So if you look at the block diagram here, while this instruction has gone into this register file for its decoding, the control unit is decoding the exact same instruction, right? And it is trying to figure out, and it is figuring out that, okay, the ALU control is actually trying to do an addition operation. So if you look at this, right, it will take some time. So you have to wait for the memory read, okay. So if you look at this, this will take some time like this, right, and finally it will settle to the add instruction that you see here, okay. This will be add. That is going to go into the ALU. Now remember that this signal is actually not going to decide the operation that's going to happen in the ALU. So you look at this, in fact it is in the next cycle that the instruction is going to get executed. So the fact that this is an add instruction needs to be transmitted across the flip-flop to the next signal, and that's why this ALU control here that we see, right, gets registered and comes out as ALU control E out here, okay, and therefore the A, what you have to now keep track of is ALU. So this is D, control E, execute, right? So the fact that this is an add instruction, right? It, so this, at this point, right, it's the program counter that is launching something. That is still the launch flop, and then we are looking at the capture flop being this intermediate flop after the register file. Okay, so the program counter is where we are starting. Then you go through the data memory and come out. Anyway, so this ALU control E signal, right? What it is in the first clock cycle, I don't know. Okay, I'm not worried about it. So I will only look at it. So as soon as the clock edge, second clock edge goes high, right, you will receive this ALU control D signal, and that will settle to its final value after a TPCQ delay. Okay, so therefore this is my ALU control E, and this is going to be my add signal that is going to come to my ALU, right? Now what is going to happen? You need to, of course, the data which is gone, past this flip-flop, the RD1E, RD2E are the signals that are going to carry the register data into the ALU. So that also will get read out from the register file. Okay, so in this portion, right, if you look at it, my A1 and A2, right, are the addresses that are going to decide in the register file which registers are going to be used. It turns out in this instruction, we are going to deal with S4 and S5, right? So therefore, what will happen is your S4 and S5 will get set appropriately, and that's what we have marked here, right? This S4 and S5 goes through the register file. The contents of S4 and S5 come out of the register file on to which signals? On to these signals. Let me mark that. I will call this as RD1D, RD2D. They will appear at RD1D and RD2D. Then you apply, go through the flip-flop and then register that data onto the RD1E, RD2E. Correspondingly, the ALU control also would have gone high, would have gone to would have settled to the right value to choose the correct operation, and then you go ahead and perform that operation in the ALU, right? So therefore, this S4 and S5 are, signals that are coming out to the ALU. Contents of S4 and S5 have come out to the ALU through the RD1E, RD2E, and the ALU control has also got registered to add. The add operation can be performed in the ALU. It will take TALU for it to sort of perform that operation, right? And then it is going to come out. It is going to bypass the data memory, come through that MUX, and this data needs to get written back into my register file. So that is a very important part, and let's look at how the signal is going to flow even for that. Okay, so if you look at this, what we are now talking about is the register file data WD3, right? If you trace this particular signal, A3 is coming like this. From which point? It is coming from this RDE, actually RDE signal, and RDE is actually going to come from where? From the instruction itself. We know the instruction, so therefore the RDD will get registered, go into RDE, and then that has to come back, right? So if you look at this, the RDD, let me just mark that here, right? If you look at this, the RDD signal, that is the destination address in the decode phase, okay, is going to first get, is already there from the instruction. So, it will just settle to its final value very quickly, right? And in this case, this happens to be what? S8, right? But it's this RDD signal is now going to change in the next operation, right? And that is anyway not going into my register file address. That is the RDE. So if you look at it, the RDE, okay, just to refresh your memory, RDE is basically this signal, RDD. We are saying all this is just RDE, right? So it's coming back there, and RDD is going to get delayed by one cycle, and therefore this again I do not know what it was in the previous cycle. So as soon as you this thing, after a TPCQ, you will get this to be what? S8 again. This will be S8, right? Now what you are trying to do, right, is to write the data back. So the addition operation has been performed, okay, and if you look at this whole ALU result, right, if you look at it, the output of that is called ALU result, and it just comes out of all this, and then the result W is what is going to go into this WD3. So you look at this guy, it is going to come from this result W, right? Or I can just call it result E, because there is no write back stage, it's called result E. So I will call it result E. Okay, that's what I am going to call this. I will call this result E. Okay, that is going to come back into this register file for writing, and therefore again what this is in the previous stage I do not know, but the result E here is basically going to take some time to evaluate, because you look at this, on the second clock edge data is getting latched for RD1E, RD2E to get its right data, then it's going to go through the ALU, then the result is going to come out through that MUX, and therefore it will take some time. After the clock edge, the ALU has to work, then the MUX has to pass it, and then it will take. So it will take quite a bit of time if you look at this. So I would say this will take some amount of time and settle to its, remember this result E is a 32-bit number, and this is going to perform. So finally at this point you will get the S4 plus S5 answer, which is available in your result E register. Okay, and where does this have to be written back? Into S8. So now what you notice is these signals, the E signals, have all lined up well. You wanted to do add S8, S4, S5. All these signals in that execute phase have lined up well. If you wait long enough, I think that is the most important part in a combinational block. If you now sample this at this point, you will get a wrong data because my ALU has not finished execution. Okay, so the key point is, if you wait long enough in a combinational block, sample it somewhere very close to the other edge, right? Of course, you cannot sample it past T setup, so it has to be T setup before that. You will be able to get the right answer, and that is what we want to write back into this whole into this register. Okay, so now what you see here is the write enable signal, right? Where is this coming from? It's basically, if you trace this signal, it's going all the way like this, right? It's going to come all the way from reg write E. I will just call it reg write E. For me, all these signals don't exist, right? We have already bypassed all these control signals. All these things we have bypassed, right? So therefore it is for me just reg write E. Okay, so this is what I have, but I need a little more space now, and therefore let me try to move some of this right, okay, this looks okay. I will call this result E as usual. Yeah, I will call this result E. Okay, and where is my right reg right E signal, right? So reg right D again is going to get decoded. So if you look at reg right D, that is going to get decoded in the first clock cycle itself, right? And this will enable it to go high right here. Sorry, right after. So it will be 0, assuming that there was no register operation earlier. This will go high. Okay. Now, and reg right E is going to be a delayed version of this, right? So therefore, you see reg right E, it will happen in the next clock cycle like this. Okay, I am just drawing reg right E and D in the same thing. So this is my reg right E signal, just a delayed version of that. So add has been performed, S4 plus S5 is now available. So if you look at result E, reg right D, okay, and the RDE, these are the three signals that are actually going to the register file. And if you look at that, so if you look at my register file, right, I have my write enable here, okay, then I have my WD3, the data in the third port and address of the third port. This is where I am getting my RDE, destination register in the execution cycle, and this is basically where I am going to get, maybe I will put this in magenta to keep the color coding, RDE, okay, the input, and then you are looking at reg right result E, because that is going to carry the answer of S4 plus S5, and the write enable is going to get controlled by the reg write E signal. Okay, so now if you look at the register file in this particular cycle here, these three signals have got lined up very nicely. Okay, so remember that the next instruction could be something else. Okay, it could be a load word where there is no register write. If there is no register write, then what will happen? This reg write D signal in that phase will simply go down to 0, right? And likewise all this will happen, right? So that's exactly what is going to take place here. Of course, because the next instruction is also a subtract, which is an R type of instruction, there is a register write back, you are going to do exactly this. Reg write D will remain high, so will reg write E in the next clock cycle, right? But anyway, so this data is going to get written back into the register file. However, remember that we are dealing with a sequential write operation. The read in the register file was combinational. Of course, we put a flip-flop after that, and therefore that made it sequential after, beyond that. However, the register file read is still inherently combinational. So in some sense, there is an important thing here. Let's call this clock, and we give clock here. Remember, this clock is what? This signal. This is what is controlling every flip-flop, register file, everything in the system. And we are assuming that the exact same clock goes to every single node in the system, and therefore there is no delay. So all these edges go up together, and therefore everything is expected to happen almost, at least ideally, together. In reality, there will be a small delay, skew and all will be there, but ideally we do not want that. So what does this whole thing of reg write going high and say, okay, go back and write this result into the register file, right? So now it means that when reg write is, asserted, you have to wait for the next clock cycle for the write to happen. So if the clock cycle 3 never came, even if reg write went high, nothing would happen. That is the key point that we have to remember here. Okay. So therefore, when the clock goes high, the register data will get written with the contents of S4 plus S5. So the register S8, right, will have junk data. I don't know what it has until the point the third clock edge actually arrives. Okay, and once it arrives, it will try to, it will write that data in, and it will take some time to write it, because it has to go through that, there are delays associated with the register file also, right? But anyway, so now what we are trying to do in this operation is we are trying to use the register S8 into which S4 plus S5 was written as the source argument for an immediate next instruction. So the immediate next instruction that we want to do is a subtract. So if I continue this waveform here, right, this ALU control will fetch the next instruction. It will take some time to decode, and then it will tell you, okay, this is a subtract instruction. Okay. Now RDD, right? What is RDD? That is going to be the destination for this. Okay. However, what you see is you want this guy to be S8 in the next cycle to the ALU. Sorry. In the next cycle, you want that to be S8. So that means the instruction that came in for subtract will have register S8 decoded. The register file gets that, and then it is going to read out that data from S8 and give it out here. Okay. So that is the key point that I am trying to highlight here. So what we ideally want is that the register S8 reads out S4 plus S5. Okay, so we want this particular result here, okay, to be available as the output that is read out of S8 in the subsequent clock cycle, right? Now that is what we have to see if it is really going to happen. So let us just complete these control signals. RDD, right, is basically the destination register for the subsequent instruction, and for this instruction it is going to be S2. So therefore this is S2, right? Now the result E here, is supposed to have, it is supposed to get that can happen only in the third clock cycle for the subtract instruction, because in the second clock cycle it is only the fetch and decode that is happening. So only the D signals will get set correctly, right? The reg write D, for example, here will continue to be high because it's a R type instruction. The reg write E will continue to be high again in the next cycle because that is a thing, right? So now let's populate all the E signals, that is in the execute phase for the second instruction, right?